In the last unit, we learned that the derivative of a function f of x tells us about the direction and speed of change at any given point on that function. Another way of thinking about that is to say that the derivative tells us about the curvature of the original function. So how do we use that information in deep learning? When we're working with tensors, all the various functions that we apply to our tensors are called tensor operations. The good news is that tensor operations are all differentiable. The derivative of a tensor operation is a gradient. An example of a tensor operation is a loss function. If we wanted to calculate this, we'll see that the loss is dependent on the input and output. But since those elements are fixed, the loss is actually just a function of w, the weights and biases of the neural network. We'll call the current values w0. Just like a derivative of f of x described the curvature of the original function, the gradient f of a given weight matrix w0 can be interpreted as the tensor describing the curvature of the function of w around that weight. This is exactly what we just said with the simple function of a line, except now our functions are much more complicated, and instead of having one or two parameters, we have thousands to millions. So there is no way to visualize this. We just can't imagine that many dimensions. But for mathematics, it's all just an extension of the same problem. If we remember the analogy with the origami rhinoceros, you'll get the picture. We're just conducting complex geometric transformations. Remember, our goal with using derivatives is to find the minimum of the original function. Given a differentiable tensor operation, it is theoretically possible to find its minimum analytically, just like what we said with f of x in the previous unit. That's like the simple example we just saw. We know that a function's minimum and maximum values are where the derivative is 0. This would be done by solving the equation gradient function of w equals 0 for any given w. Of course, we don't know the actual function. That's the whole point. That means we have to turn to the second approach and try to incrementally approach the point where the derivative equals 0 by moving the parameters w0 in the opposite direction of the sign of the gradient. Remember, the gradient of f of w0 can be interpreted as the tensor describing the curvature of the original function f of w around the point w0. In our case, the function for which we want to find the global minimum is the loss function, categorical cross entropy. We do this by adjusting the weights in the opposite direction of the gradient. We'll also adjust the amount we adjust the weights by a scaling factor called step. The gradient only approximates the curvature of the original function when we're close to 0. If we're really far away, we'll adjust the weights too much and can potentially end up far from the minimum. We'll see this in action in a minute. This is termed gradient descent. Descent, since we're trying to find the minimum of the loss function. More specifically, it's called mini-batch stochastic gradient descent. To understand this term, we need to return to step 1 in our 4 steps of deep learning. Recall that instead of using all the values to calculate our loss function, we just used mini batches of 128 samples. Stochastic just means that we chose these 128 samples randomly. So why not just use all 60,000 samples to compute the loss function? 128 sounds pretty lame compared to 60,000. There are 2 metrics to consider here. One is the accuracy of the model, that is, how close we are to the true minimum of the function, and the other is how expensive in terms of computing power and time the calculation takes. We're talking about the risk of overfitting our model to our specific training set. Batch gradient descent uses the entire sample, which means we have high accuracy, but also the highest expense. If we go to the extreme opposite end, true gradient descent uses only a single sample. Although that is very inexpensive, it's also going to result in a low accuracy. Mini-batch stochastic gradient descent is a happy compromise between the two that allows us to converge on a reasonably accurate minimum value with an acceptable expense, and is essential for large redundant datasets. That's what happened in the first step when we ran our model. In the second step, we have an initial forward pass. We need to start somewhere, so that's why we just used random parameters for the first forward pass. In the third step, we calculated the loss function, categorical cross entropy, as well as the accuracy metric. Then we proceeded to step 4, gradient-based optimization, where we now applied the process of mini-batch stochastic gradient descent to adjust our parameters. Now that we know what mini-batch stochastic gradient descent is, we need to cover a couple topics to understand how it's applied to modern deep learning. I'll cover that in the next unit.